Okay, for our second part here, we're going to look at a couple of concepts here that come up when we have continuous functions, or not continuous functions, that is. And the first thing that we're going to look at here is just being able to identify certain continuous functions. Okay? And if you look at page 77, turn back there. There's some specific information about what types of functions are always continuous. If you look right below example 3, the functions mentioned are the following: a polynomial function. Okay, polynomial functions are always continuous. Okay? So in terms of an always situation, it's always polynomials in terms of being continuous. Okay? So any power function, okay, or combination of power functions, okay, 4x squared plus 2x plus 3, that's a polynomial, it's continuous. Okay? All rational functions are continuous, except when the bottom equals 0. Simple terms. So any rational function, which is a polynomial divided by a polynomial, is going to be continuous except for when the bottom equals 0. So that one that Chris mentioned, 1 over x squared plus 1, that bottom can't ever equal 0. And it's a rational function, so it's always continuous. There is no bottom equals 0 worry in that one, so we're good to go. All right. The other types that are always going to be continuous, okay? The absolute value function, which we know has a V shape to it when we graph it. Well, not segments, but rays. Exponential functions, logarithmic functions, trigonometric functions, namely sine and cosine. Anybody think of why all of them aren't always continuous? Why is tangent not always continuous? What does tangent have? It's got asymptotes. So sometimes, depending on where the asymptotes are, sometimes tangent, cotangent, secant, cosecant are. Okay. Really basically anywhere except for where there's asymptotes, those are going to be continuous. Okay. All right. Most radical functions, like something like the nth root of x. Okay. So radical functions. And again, keep in mind that all these functions that we've studied in the past, okay, are going to be continuous, except for where we have points that give us domain issues, essentially. Okay, if there's any points where we can't put 0 on the bottom, etc., okay, then we're going to have a problem at those particular points. Okay? But most of the basic type of functions that we've studied since algebra class, okay, are going to be what we call continuous functions. Okay? And like I said, some of them might have some issues if we have asymptotes, etc., but ultimately most of those are always going to be continuous. Now, what's nice is that if we take any of these types of functions that we mentioned, say for instance if we take e to the x plus x squared, okay, and we know that e to the x is continuous and x squared is continuous, what might be able to be said about the result of the sum of those two? It's continuous as well. Okay, and we actually had that formalized in a theorem on page 78. If you take a look at that, it tells us exactly that if we have two functions that are continuous and we add them together, we get yet another continuous function. Same thing with a difference, a product. If we were to subtract these or multiply them, same thing. Okay, the only thing that we can, as we can imagine, is the quotient part. If we were to take e to the x and put it over x squared, that would be continuous except for where the bottom equals 0. So in this case, it would be at 0. Be an issue. All right. And if we took, say, x squared and we multiplied it by 3, okay, a constant multiple, okay, would that change the continuity? No. Okay, we know that multiplying by 3, all that actually does is just stretch the graph anyway, or shrink depending on what you multiply by. Okay, so it doesn't change the continuity part. And then in theorem 7, okay, we have a pretty powerful theorem that talks about the composition of two continuous functions. So for instance, if I had, let's say, e to the x, but I had an absolute value around it, okay, the question is this continuous? And we could say yes, by theorem 7 it's continuous because we're composing we're putting a continuous function into another continuous function, and if that's the case, the result is also continuous. So that theorem 7 guarantees that if we compose two continuous functions, okay, we have yet another continuous function. So another example of that would be if we took, let's say, sine of x and we squared it. Sine of x we know is continuous. X squared we know is continuous. So therefore, what can be said about the sine of x all squared? It's also continuous. And what theorem tells us that? Theorem 7. Okay. All right. And the final two parts that we're going to look at, okay, are I mentioned earlier that we're going to talk about that idea of the fact that those discontinuities are removable. Okay. So we're going to check that out next by looking at the exploration on page 77. Okay. And we're given this function to work with, and we can see that it's a rational function, so there may be some domain issues, and we know that 3 and negative 3 would both make the bottom 0 here, so we know that those are the two problem points, if you will. And so the question then, number 1, it says factor the denominator, and then what is the domain? Well, we know that factoring the denominator, it's a difference of two perfect squares. So the domain here would be everything but negative 3 and 3, and remember we indicate that with interval notation. To list the domain of this function would look like that. Again, keep in mind it's parentheses around the 3 and negative 3 because if we use brackets that would include those. We don't want them included in the domain here. So ultimately that gives us the whole line, negative infinity to infinity, except for negative 3 and positive 3. Okay. So that would be our factorization in our domain. Okay. And then number 2 says investigate the graph of f around x equals 3 to see that f has a removable discontinuity. So let's take a look at the graph here. Zoom in a minute. Put in my x cubed minus 7x minus 6. And then, oops, squared minus 9. And if we do our zoom 6. And notice that it told us to investigate 3, because we can see at negative 3 it's clearly an asymptote. Okay, but if we look at 3, the question is investigated to see that it has a removable discontinuity. So we can't really see an actual hole here in the graph because the calculator is, unless you have it set up perfectly, it won't actually show the hole. But we can definitely see the hole if we did the table. Okay. If we scroll down in our table and find 3, we can see that it's an error there. And if we zoomed in closer than that, we can see that it looks like the answer somewhere between 2.8 and 3.8, obviously. Again, if we made the scale smaller, we would see a nicer approximation of what it equals on either side of that, of course, by 0.1s, etc. And we can do that, but we'll leave that alone for now. But we can see that it's a hole both by graph and by table. And then part 3 says, how should f be defined at x equals 3 to remove the discontinuity? So, knowing that we have a hole at 3, right, here's what we want to write for ourselves in order to remove the discontinuity. Okay? Because if it's a hole, okay, we can remove the discontinuity by essentially filling in the hole. So this is our function currently, and what we're going to want to do is we're going to want to make a new function, okay, that is this function for everything except for 3. And then what we want to do is we want to write it, essentially as a piecewise function, and we want to redefine what's going on at 3. Okay, so we still want the function to be normal, okay, what we were given, at everything but 3. But then at 3, what we're going to do is we're going to fill in that hole by assigning a y value to x equals 3. Now the question is, what y value should we choose? Okay. What y value would fill the hole in general, not just in this problem? What would the y value have to be like? What would it have to be the same as? Alright, so how do we say that in math, the same as where the hole is? That y value would have to be equal to the what? The limit. Be equal to the limit at that point, wouldn't it? So if we could find the limit at that point, then we would know what to put in that blank then, wouldn't we? So the question is, can we find the limit? Well, we know that by direct evaluation, okay, we can't find the limit. So therefore, can we do some algebra? Well, we already did algebra on the bottom one. Now, can we do something with the top? They told us, and we should know at this point, that if this 3 gives us a whole, there must be an x minus 3 factor up there, because that's the only way we'd possibly get a whole, is by having these two be able to cross out. Okay, so the question is, what's the rest of it up here then? Okay, what is the rest of that number up there? And you could either do polynomial long division, okay, or you could do synthetic division and divide. We get 1, 0, -7, and -6. And so if we divide that to see what the other factor is, knowing that one factor is x minus 3, where the procedure for synthetic division is bring down our 1, multiply by 3 and put it here, add, multiply, and we get a 0 remainder, which is good because we knew that was a factor. And so therefore the rest of the factor would be x squared plus 3x plus 2. So if we can successfully factor that top, and we know that those two cross out, then our new function that we're going to try to find the limit for is x squared plus 3x plus 2 over x minus, or x plus 3 that is. And now, if we want to find the limit as x approaches 3, we can plug in and see what we get. We get 9 here, 9 here, 2 here, that'd make 20. And then 3 here, give us 6 on the bottom. So the answer would be 20 over 6, which reduces to 10/3. And so that right there is going to be what goes in the blank. So ultimately, the way we fill a hole, the way we make a function continuous that's not when we have a removable discontinuity, is that we essentially redefine the function. Okay? We let it be normal for everything but the point in question. And then that point in question, okay, we fill in the blanks by defining a y value here. Okay? And remember, if we just put a number here, and it's just 1x right here, all that represents is a point. Okay? This part on the bottom just represents the point 3 and 10/3. Okay? And if we were to plot that, okay, we would see everything we just saw on the graphing calculator, true? But it would have a hole in it. Okay? And then if after that we plotted this point, okay, what would happen? That hole would get what? It would get filled. Okay? And so what we've created here is what we call an extended function. And we're going to be asked in our homework here to write some extended functions. And so our procedure is going to be exactly what we just did right here. This is an extended function. So we're going to rewrite the given function in terms of itself at whatever point in question we ever have in the whole issue. And then here, figure out what is going to be the y value that would fill that hole. And what is the y value in general? It's the limit at that particular point. So with our limit techniques, we're going to find that limit, and we're going to fill in that hole once we find the correct value. Okay? Questions so far? All right. Now, there is one final part to our work today, and that's what we call the intermediate value theorem. And we've worked with the intermediate value theorem before, and I'll give you an example of how. Okay. In algebra, we might have had a chart like this, let's say an XY chart where we had 0, 1, 2, 3, 4, for instance. And we had -3, -2, 1, 2, -6. So let's say the chart looked something like that. Okay. The question that we're looking at here is if I'm at 0, -3, and then I'm at 1, -2, and then now I'm at 2, 1. Okay, what had to have happened between x equals 1 and x equals 2 if the y value changed from negative to positive? Okay, what did we do on the graph? Across the x-axis. So we ultimately have used this principle here to recognize where we'd have zeros for a particular function. True? We'd also have a 0 between these two because it changed from 2 to 6. Now there's a very important part that this relies on that we didn't investigate in Algebra 2 or Pre-Calc, and that's the fact that there is a stipulation for this to be true. For us to actually have a 0 between those 2 points, there's got to be something about the function that is true. Because if you look at the graph I'm about to make right here, if I went 0, -3, that's right there, 1, -2, that's right there, and I went 2, 1 right there, okay, would there be any reason why I couldn't do something like this? Okay. That would satisfy all 3 of those points I mentioned, wouldn't it? Okay. But would there be a 0? No. Okay. There's no 0. But we said, wait, it changes from negative to positive. How come there's not a 0? Well, what is it about this function that makes that not true? The function is not what? It's not continuous. Okay, and the intermediate value theorem, using that principle to investigate this, relies on the fact that we have a continuous function. And if we don't have a continuous function, then there's no guarantee from this chart that there is a 0 between any of these 2 points. Fair enough? So what that intermediate value theorem guarantees, and you can read it with me here, theorem 8, it says that a function that is continuous, and that's the key word there, on a closed interval a to b, takes on every value between f of a and f of b. In other words, there is a y value between f of a and f of b, such that f of c equals that y value somewhere in the interval. Now, that sounds rather complicated, okay, but all it really is telling us is this. Okay? If you take a look at this second picture, let's just say I have this point right here, just for argument's sake, let's say that's the point 1, 6. So if I have the point 1, 6, and in some manner I make my way over to the point, let's say 7, 2, okay, and I can see that this is a continuous function. Would you agree? Okay. All the intermediate value theorem guarantees is that if this is continuous, that somewhere between 1 and 6, or excuse me, 1 and 7, okay, in the x direction, between 1 and 7 in the x direction, okay, somewhere this function hits every y value between 6 and 2. So that means there's an x that's going to have 5 as a y value attached to it. Okay, in other words, if I were to draw y equals 5, would the function hit it? Yeah. If I drew y equals 4, would the function hit it? Yeah, it's between 2 and 6. What about y equals 3? Yes. Okay, what about y equals 7? In this case, it looks like it does, but does the theorem guarantee it? No. Okay, it could go outside 2 and 6, but we know that everything between 2 and 6 has to get hit. Okay? And therefore, like I said in this part, that's why if I go between negative 2 and 1, what strategic number has to get hit based on the intermediate value theorem? 0. Okay? But again, it all relies on the fact that this function is continuous. Okay, that we're going to work tomorrow on the rest of our homework.